Okay, so in that last video, we finished off showing us graphically what the Otto cycle looks like. Again, this is an idealized air cycle where air is the working fluid, and it mimics what we call a spark ignition engine or spark ignition process, which we see in internal combustion engines for the fuels like gasoline, compressed natural gas, occasionally propane, but anything that has what we call a spark plug, right? So what does that look like here? Well, some terminology we should mention. Let's talk about some terminology. So I'm not a huge gearhead, if you will. I'm not real big into cars. I understand how they work and I can work on one when I need to, but it's um, but I do need to explain some terminology. Um, so top dead center and bottom dead center. And if we go back and look at the Otto cycle diagram, notice there's BDC and TDC is showing up on the volume axis. It's referring to these two situations here. Top dead center is when the piston forms the smallest volume in the cylinder. And bottom dead center is when the piston forms the largest volume in the cylinder. And it might be hard to think about that because we're typically thinking about a piston where it's like this and the piston's moving up and down like this, where we've got a cylinder and the piston's moving up and down inside it. In an engine, it's actually flipped. Your piston is like this. I'm sorry, your cylinder is like this, and your piston moves up and down this way. And so think about it that way. And I've got it visually here on the next slide. So top dead center being the smallest volume, that's when the piston is up here at the very top of the cylinder. Again, it's kind of flipped around from how we've been thinking about it back in chapter 4 and beyond. This is how it is actually in an engine when the contents is not going to get to the liquid form. In a liquid form, you want that cylinder flipped like this because all the liquid can collect to the bottom or a mixture can collect to the bottom. Here, everything's gas, so we can actually flip it up. And then I've got valves in a real engine. I'm going to have valves on the top that allow us to bring in new air fuel mixture and exhaust. Then the other valve can open up and kick out the exhaust gases back out. So that's how it looks in a real engine. And we're going to use those terminologies here. So top dead center refers to the smallest volume, and bottom dead center refers to the largest volume. The what we call the clearance, or I'm sorry, the displacement volume. So the clearance volume is just simply the volume that's top dead center. Now, but the displacement volume, that's a term that you'll see from time to time. The displacement volume is the difference between the max volume and the min volume, which again, that is the bottom dead center volume minus the top dead center volume, right? So when you go to purchase a car with an internal combustion engine in it, and they talk about the engine, and you get a specification on it, you'll see a number in modern cars, you'll see a number of liters. In older cars, you would have seen a number of, in the United States, you would have seen a number of cubic inches. In both cases, that's a volume, right? That's a measure of volume. What does that number mean? That is the displacement volume for the entire engine. So if you go buy let's say a small sedan with a 2 liter, let's keep the math easy. Let's say a 2 liter four-cylinder engine in it. That's a fairly standard size. They're a little smaller today, but that's a fairly standard size for a nice large car. It's 2 liters for a four-cylinder engine. What they're saying is if there's four cylinders, a total displacement of 2 liters, each cylinder has half a liter. And what does that half liter mean? Well, a half liter means each one of those cylinders in that car has a difference between its top dead center and bottom dead center, the max and min volume. That difference is half a liter for all four of those cylinders. So all four of those cylinders combined together to be a 2 liter displacement. Okay. So that's what those terms mean. They have real world meaning, not just here in the book, but that's what they're representing for us in the textbook. Okay. Now I'm going to go forward here. Let's explain a couple of other terms. The stroke is the largest distance a piston can travel, and the bore is the diameter of the piston. If I go back a slide, and let's go put those on the diagram here, the stroke would be the distance from here down here, this is what we call the stroke. That is how far the piston travels to get from bottom dead center to top dead center. And the bore then is the diameter of the cylinder. Sometimes you'll hear people that work on, especially older cars, you might hear the term boring out the cylinders. What they're actually meaning is they're actually using a tool to go in and cut a wider cylinder, in basically increase the displacement volume so they potentially can get more power out of the engine if they go back and get everything fixed right. It's a pretty intensive process, but some people can do that if they've got the right tools. And your engine has thick enough walls that you're not going to blow them out by thinning out the walls. But anyway, I digress. Another very important, probably the most important term we've learned so far is this one here, the compression ratio, the R value. The R value is the ratio of the maximum volume to the minimum volume. That's the compression ratio. What is basically, it's a comparison of the volume at top dead center to the volume at bottom dead center. It's another way of, it's more important than the displacement volume is mathematically. We'll see that in just a little bit, but they're kind of describing the same thing. They're describing the difference, in this case, the ratio between that max and the min volume. Okay, so these are terms we have to be aware of. Now, if we look at the actual engine that this represents, or what an actual engine might look like, an actual spark ignition engine. So an actual spark ignition engine looks something like this. And I think I've got this on the next slide. Let's see if this comes out. Yeah. So an actual engine, you've got injection, then compression, and then what we call the power stroke, and then exhaust. So it brings in an air-fuel mixture, compresses it, hits it with a spark, makes it blow up, and then it kicks out the spent air-fuel mixture. And then the process repeats over and over and over again. This is what any one of those cylinders in your internal combustion engine, if you're using gasoline, or you have anything that has a spark plug in it, a lawnmower or weed eater that's gas powered, they're all doing some version of this. This is what we call a four-stroke process. There is a two-stroke process where it's not, where there's four parts of this process. And you can go Google two-stroke GIF and see the kind of the difference. They're very similar. It's a little simpler process. The two-stroke is easier to do in a small package. That's why we see two strokes in like weed eaters and chainsaws. Anytime I've got to add oil to the gas, to the fuel, that's going to be a two-stroke engine, where this is a four-stroke engine, because in the four-stroke engine, you've got a separate compartment down here I can have oil in. In a two-stroke, the geometry is such that there's no real way to have a separate lubrication compartment. So you actually have to put the oil into the fuel, and the fuel also serves as a lubricant in a two-stroke engine. Okay. Anyway, that's more than we really have to know here. I'm going to go back a slide and let's look at this process, what this looks like. So, and I've just pulled information off of Wikipedia, nothing fancy here, and that's where that GIF is from. But notice that there is this, you've got the expansion, and then it goes down here, and this is kind of the exhaust and the intake, and then it goes back up and compresses, and now it's ready. And then you ignite, and it burns, and it gets all the way around the cycle, and it expands, and that's the process. Okay. Now, if it's purely reversible, notice that I've got the secondary loop down here. Right? Notice I've got the secondary loop down here. And if I if I compare the two side by side, one might look at this and say, Steve, these don't look the same at all, right? Well, actually, notice that I've got the secondary loop down here. The top loop is expansion on top and then compression on the bottom. So this is work out. This top loop is work out. This bottom loop has compression on top, expansion on bottom. Remember, the signs on these are different. Expansion is work out, compression is work in. And down here, this is expansion is work out, and compression is work in. So compression is work in, expansion is work out. So notice that these have two different signs. This top loop is work out, this bottom loop is net work in. But if it's reversible, if the process is reversible, there will not be, I apologize, I'm getting a phone call. Okay. So we were talking about this secondary loop down here. If the process is reversible, right? Now notice if the process is reversible, what happens is this ends up just going back and forth, right? So basically what we're saying is you would have, oh, back, I apologize. There we go. You would actually have that secondary loop down here, but it would be just a line. There would be zero area. It's reversible. So it would be back and then forth and then back and then forth, right? So we don't actually count that because the whole process is reversible. So it's all that to say that's if you take away this bottom loop, notice that these two diagrams very, very closely mimic and match each other. Just understanding that as we approach reversible, the area of this secondary loop approaches zero. Okay. All right. So again, the Otto cycle we're going to use to be a very good approximation comparison of what would a perfectly ideal reversible internal combustion engine using a spark plug, what would that process look like? The Otto cycle is what we will use to do so. So we talked earlier about what are some common air idealizations that we will employ, and these are the ones that we will employ for the Otto cycle. It's the same list. We're going to use air. We're going to treat it as an ideal gas. We're going to not bring in new air with new fuel and burn it and then exhaust that out and bring in more. We're not going to be constantly bringing in mass and kicking mass out. We're just going to have a bubble of air. It's going to be in a closed system, and we're just going to trap that air in a piston, and we're going to heat it up, and then we're going to cool it down. We're going to heat it up, and we're going to cool it down. And it's going to expand, and we're going to compress it, and it's going to expand, and we're going to compress it. Right? So these are the simplifications we're going to employ for the Otto cycle that will make this a good approximation for a real internal combustion engine, but not perfect. We acknowledge that. It's not perfect, but it's a very good approximation. Okay, so we saw these in the diagram. Here they are again in words. Isentropic compression from state 1 to 2. That again, it's compression, so that's work in. So we're taking the work in, replacing it with work from 1 to 2. Constant volume heat addition. So that's heat in, that's heat from 2 to 3. So heat in is heat 2 to 3. So we're basically looking at what the first law for the whole cycle looks like. Isentropic expansion, that's work out. That's work from 3 to 4. So that's minus work out over here. And constant volume heat rejection. So that's heat out. That's the heat that occurs from 4 to 1. So this, again, is a cyclic process. So the change in U is I'm going from I'm going to finish at U1 and I'm going to start at U1. So for the whole cycle, the change in internal energy is zero. That's a cyclic process. The change in internal energy for a cyclic system is going to be zero. Very, very important concept here, very commonly used concept we need to talk about here is what we call the thermal efficiency. Now, it's true for any engine. It's always a comparison of the work we're going to get out of the engine compared to the heat that we have to put in to get it. And so it's a comparison of how good is this engine at converting heat into work. We can, because it's an ideal gas and because everything's reversible. Remember, there was that K ratio that showed a ratio of temperatures can be approximated as a ratio of volumes to the K minus 1. And we basically can employ that here. And remember, R is just the ratio of volumes. So 1 minus 1 over the ratio of volumes to the power of K minus 1 gives us essentially the same value we would get for the thermal efficiency because it's reversible and it's an ideal gas. And so notice what's happening here. As R increases, as I increase the compression ratio, this quantity is increasing. The numerator of this I'm sorry, the denominator of this fraction is increasing. As the denominator increases, this negative value gets smaller. So I'm subtracting from 100% a smaller and smaller value as R increases, the efficiency increases. So if I can get the, a larger bottom dead center volume and squeeze it up to a much smaller, and that's normally how I would increase my compression ratio, is squeeze it up to a much smaller top dead center volume before I hit it with the spark. That's a very good way of increasing efficiency. If I'm not careful, it's also a very good way of blowing my engine up, but that's another discussion we'll have in the next couple of discussions here. Last term to talk about here, what we call the mean effective pressure. This is, I say it's fictitious. I like to say you're probably never going to encounter a mean effective pressure value outside of a thermodynamics textbook. And this is really all I want to talk about here. The big thing is the mean effective pressure is if I know the network for an engine and I know the displacement volume, I can calculate the mean effective pressure and vice versa. It's a simple equation, three terms there. There's a reason that I could show you the derivation. I just really don't like spending a lot of time on it because I really genuinely think that outside of a thermodynamics textbook, outside of a classroom, I'm not really sure it has much value. But it's a value. So you will encounter, I at least mention it because you will encounter some problems in the text if you're picking problems to practice where you'll see a mean effective pressure value. Okay. So really, that's all the class time I want to spend on that. If you have questions, please let me know. Send me an email, leave me a comment. I'll do my best to try to point you in the right direction. Okay. All right. Where does that take us? That takes us up to an example. I'm going to stop here. I'm going to talk about the diesel cycle before I tackle this example problem. So that's what the next video is going to be, is about the diesel cycle.